Welcome. In this lecture, we do a quick recap of the linear algebra notions that will be useful for lattice-based cryptography. Since this is a course where we assume prior knowledge on linear vector spaces and matrices, I refer to all elementary linear algebra textbook for a formal introduction. Now, as we recap those notions, I want to make sure that we see things in general, in particular, the fields that we'll be using for the description of our linear vector spaces might not be the field with real numbers, as it's sometimes restricted to in introductory linear algebra. So what is a field? It's a set equipped with a multiplication and an addition. And for the addition, it is a group. So we have that both multiplication and addition are associative, and the as a group, the addition as an additive group, the vector space is commutative, and also as the multiplication is commutative. Now there are neutral elements, 0 and 1s. So 0 being the neutral element for the addition and 1 being the neutral element for the multiplication. So every element of the field has an inverse for the addition, and every non-zero element in the field has an inverse for the multiplication. And very importantly, there is distributivity of the multiplication over the addition. So one of the most famous example, of course, is the real numbers equipped with the traditional addition and multiplication. Now, some of the fields that we may encounter in this course, in this module on Euclidean lattices, are the prime fields. So let P be a prime number. The residue classes modulo P form a field where the addition and the multiplication are the addition multiplications that we defined for residue classes modulo an integer. And also, we can define more general finite fields that are extensions of those fields of the form Z mod PZ. Now, with that in mind, we can define vector spaces. So a vector space K, let K be a field, V a vector space, is a set equipped with an addition, and so an addition between elements of V, and a multiplication between the elements of K, which we call the scalars, and the elements of V. And that maps those multiplications to V. So the important properties that those addition and multiplication need to possess, first of all, that the addition needs to be associative, needs also to be commutative, and it needs to be a neutral element. So in other words, we have ourselves an additive group. And in addition, the external multiplication, so the scalar multiplication, needs to satisfy that whenever we multiply lambda to mu times v, it's the same as if we multiply lambda times u to the vector v. And also, we need to have a neutral element, so the neutral element acts trivially, okay? And we have a distributivity of the multiplication over the addition, so lambda times u plus v is lambda u times lambda v, and the same on the other hand as well. So the lambda plus mu times v is lambda v plus mu times v. So the vector spaces are called that way because they mimic the properties of vectors. So the space of vectors over field K is the perfect example of a vector space. And it satisfies, of course, if we need to define the addition and the multiplication, but if we define them in the most intuitive way, which is the addition is an addition coordinate-wise, and the multiplication by mu is also coordinate by coordinate, then we have all the properties. So we'll leave them as an exercise, but we have all the properties that are desired. So vectors over finite fields are very interesting to us. And now let's talk about how to generate a vector space. So in particular, we need the notion of the span of a set of elements. So we assume that we have a vector space, V over K, a field, and a family of elements, so a set of elements of V. We call span of S all the potential linear combinations of elements in S, okay? And that is a vector space. That's a vector space that is inside of V, and it may or may not be V depending on if S generates V. So for example, assume that we have K, the field of real numbers, and V is R3, and S is the canonical basis. So the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. So the span of this family is all the linear combinations of V1, V2, and V3. And because in this particular case, we have a family that generates all R3, we have that the span of S is simply R3. Now, the span of S leads to the notion of a basis. So a basis of a vector space is a minimal generating set. So if if S is a family of vectors, a set of vectors, and if V is the span of S, then it must be that for S to be a basis, it must be that there's no subset of S such that V is the span of that subset. So an example, let's deal with K is R and V is R3, and our previous set S, which is the canonical basis, so 1, 0, 0, 0, 1, 0, and 0, 0, 1. With that, we have that, so the set S with 3 elements is a basis. However, if I add any more elements, then this won't be a minimal generating set. So for example, here the set S prime, to which it's S to which I added 1, 1, 0. This does span V, but it is not a basis because I can take out the element 1. Sorry, I can take out the element 1, 1, 0, and it would still generate my vector space V. Now next we move to the definition of matrices. So matrices are arrays of elements in a field, and so here we denote n the number of rows, and m the number of columns. And the traditional representation of a matrix is that way here, okay? So these are just arrays of elements in your fields. Now, what are they good for? So we do many things, and we'll need those to use matrices, a lot of results on matrices throughout the lectures on Euclidean lattices. Now, matrices themselves form a vector space. I can add matrices simply coordinate-wise. I treat them as vectors. And I can multiply a matrix by a scalar by basically multiplying every coordinate of this matrix by that scalar. So as I do this, I'm really treating a matrix as a vector of length m times n. There's nothing, when we look at matrices as a vector space, there is really nothing special about matrices. They're just as good as vectors. But we can also multiply matrices. So the multiplication of a matrix is another matrix. So to be compatible, a matrix with p columns and n rows has to be multiplied by a matrix with p rows and some number of columns. And every entry of the resulting matrix of n rows and q columns, where q is the number of columns of the matrix B on the right-hand side of the multiplication, every entry is basically a dot product between, so here we have the entry of the column ij. It's going to be the dot product between the row of index I of A and the column of index j of the matrix B. And so this product does not necessarily make the space of matrices a field. Some matrices are invertible and some are not. So there is a neutral element for this multiplication, which is the identity matrix. Every time you multiply a matrix by the identity, you just simply keep your matrix. Now, some matrices have an inverse. What that means is there is another matrix such that you multiply them together and you retrieve the identity. And so in that case, we say that we have the inverse of the matrix. Now, to move towards the calculation of inverses of matrices, we have to make a detour by the calculation of what is called the determinant. So the most elementary calculation of the determinant is the determinant of 2 by 2 matrices. So it's a well-known formula that the determinant of the matrix A, B, C, D is going to be AD minus BC, okay? And that's the kind of notation that we use. Now, moving on to more complicated matrices, we need to introduce the notion of signatures of permutation. So what's a permutation? It's a bijection of the set 1n. So all the integers between 1 and n. And a permutation is, so the set of permutation we call S sub n. And so just a bijection, so mapping each element here to another element here in an invertible way. Now, every permutation of 1n can be defined by the reordering of the elements 1 to n. So sigma 1 to sigma n is going to be a shuffling, basically, of the integers between 1 and n, okay? And we define the signature of sigma as 1 if the reordering involves an even number of swaps between elements in 1n, otherwise it's minus 1. So quick example here. So 1, 2, 3, the signature, sorry, the permutation defined by the reordering 1, 3, 2, the kind of, there's only one swap required to get there, which is the swap between 3 and 2, so the signature is minus 1. Now, if we define that other permutation 2, 3, 1, then to get there, we have to permute we have to permute 1 and 2, and then 2 and 3. So we have 1, so we have 1 as the signature. So the determinant formula uses basically this notion of signature. So first we need a square matrix, and this is the determinant. So it's a sum over all possible reordering, so all possible permutation of 1n. And for each of those permutation, we take the product of all elements, so of the form A sub I sigma of I. So that's going to be a product of n of the n square coefficients of the matrix. And we multiply that product by the signature of sigma, okay? So in the case of n equals 2, we really want to retrieve the traditional determinant formula. So there are two possible permutations of 1n. One is the trivial one, where we get to this reordering by performing 0 swaps, so the signature is 1. And then the other one is the reordering 2, 1, which is obtained by 1 swap, so the signature is minus 1. So in the end, if I specify this formula for n equals 2, then what do I get? Two terms, a 1, 1, a 2, 2 times 1 plus a 1, 2 times a 2, 1 times minus 1. And that is exactly the formula for determinant of 2 by 2 matrices as we know it. Now, the more we increase the dimension of the matrices, the more complicated that formula becomes. And that's because the cardinality of Sn, because we do a sum, the number of terms is the cardinality of Sn, the cardinality of Sn grows exponentially with n. So that's what the formula looks like for 3 by 3 matrices. And we can verify that by looking at each permutation of 1, 3 defined by their reorderings. And there is a trick, sort of a visual aid, so to speak, in order to calculate those determinants, is to rewrite, extend the matrices with the first row here and the second row here, and then to draw diagonals. And each of these diagonals in blue are with the plus sign, and each of these diagonals here in red are with the minus sign. Okay, and we have all the 6 terms here of our determinant calculation. Now, we're going to use very special determinants given a certain matrix in order to facilitate the calculation of both the determinant and inverses. So cofactor of a certain coefficient, aij of a, is -1 times I plus j times aij, where aij is a determinant of size n-1, n-1, where we take a and we remove the row number of the row of index I and the column of index j. So what does it look like? So here, for example, if I and j are equal to 1, then this is the cofactor of a11, okay? And that's -1. So you see, all I had to do was to remove 1 row and 1 column, and that gave me this cofactor, okay? Now, with cofactors, we can do interesting things. First of all, we can reduce the calculation of an n times n determinant to calculations of determinants of size n-1 times n-1. Otherwise said, we can reduce the calculation of determinant to the calculation of cofactors. Okay, and so for example, for each I, we can expand the determinant. So here we sum over j, okay, and we have the sum of -1 to the I plus j aij times cofactor aij. So what does it look like? So if I take this matrix, the first, so I expand for I equals 1, so I get my first term here, then my second term, so you see now I've moved on to j equals 2, and then my third term where I moved on to j equals 3. And so my determinant here is 14, and I obtained that determinant only by calculating determinants of 2 by 2 matrices. Okay, so cofactors are useful that way. And they're also useful to calculate inverses of matrices. So we have this very important property that the inverse of a matrix, when it's invertible, is 1 over the determinant. So we see that, of course, it only exists when the determinant is invertible, times the transpose of this matrix C defined by Cij is -1 to the I plus j times the cofactor of aij. So let's calculate this. So we're going to have to calculate all possible cofactors here. So we have only 2 by 2 determinants to calculate, but we're going to have to calculate 9 of them. So C11 is -1, and then we continue. So C12, and then C13, and C21, C22, C23, and C31, C32, and C33. So that gives us the matrix C, and now we transpose C, multiply by 1 over the determinant which we calculated in the previous slide, also through cofactors, and that gives us the matrix A inverse just at the price of 2 by 2 determinants. Now, matrices are used for many things. We're going to mention two important applications. One is how to change the basis of a vector space. So a vector space can have more than one basis. And so let's call B1 V1 to Vn and B2 W1 to Wn. Now, we can always rewrite elements the elements Vj's as a linear combination of the Wi's, and also that each Wj, of course, can be rewritten as a combination of the Vi's. So if we have a vector V that is expressed in the basis B1, we can calculate the decomposition of that vector V in the basis B2 through a right matrix vector multiplication by the matrix that gives the rewriting of the Vj's as a linear combination of the Wi's. And so that gives us V in that new basis. So as an example, let's assume that you have those two bases. And so that is the basis that expresses the first basis with respect to the vectors of the second basis. So assuming that we have as an input the vector 1, 1, as in expressed by the coordinates 1, 1 in the first basis, then to express this same vector in the second basis, then we just simply multiply it by A, the vector 1, 1. And we can verify, of course, that this gives us the right answer. Now, second important application that we'll mention is linear maps. So linear maps are maps from vector spaces to vector spaces, such that for all V1 and V2 and in the vector space V and lambda a scalar, we have f of lambda times V1 plus V2 is lambda times f of V1 plus f of V2. Now, such a linear map can be expressed thanks to a matrix. So we have two bases of V and W and a linear map between those two vector spaces. Then what we can do is look at the decomposition of each element of the basis of the domain expressed as a linear combination of the basis elements of the range. Okay, and now if we have a vector V expressed as a linear combination of the vector space of the domain, then we can express f of V as a matrix vector multiplication by the matrix whose coefficients give you those decompositions. So as an example, assume that we have a very simple linear map, which is given by f of x1, x2 is x1 plus x2. Then the matrix that gives this decomposition, that expresses the images of the basis element of R2 with respect to the basis element of R, which is just one element, is the 1 by 2 matrix. So each column here is f of the vector of the basis vector. So f of 1, 0 is 1, and f of 0, 1 is also 1. And so f of x1, x2 is this matrix 1, 1 multiplied by this vector x1, x2, and that is the 1 by 1 matrix x1 plus x2. Thank you for listening. This was a very short recap of some very important linear algebra notions. And in the following lectures, we will discuss lattice-based cryptography that will heavily rely on these notions. Thank you very much.